What specific problem does the two-simplicial transformer aim to solve in the context of large language models, and why is this problem significant?
The two-simplicial transformer addresses the challenge of scaling large language models, LLMs, efficiently, under limited token budgets, which is increasingly significant as the availability of high-quality tokens becomes a bottleneck in AI training. Traditional transformer architectures often require a proportional increase in both model parameters and training data to achieve optimal performance, as highlighted by the Chinchilla model's findings. However, the two-simplicial transformer demonstrates that it can outperform standard transformers on tasks like math, coding, and reasoning, while requiring fewer tokens relative to its parameters. This capability is crucial because it allows for better utilization of computational resources, particularly when high-quality tokens are scarce. Ultimately, the two-simplicial transformer offers a more favorable scaling exponent, suggesting that it can approach the irreducible entropy of natural language more effectively than traditional models, making it a valuable advancement in the field.
How does the proposed two-simplicial transformer method work? Illustrate the methodology step by step, particularly focusing on the trilinear forms and attention mechanism.
The proposed two-simplicial transformer method extends the traditional dot product attention mechanism by utilizing trilinear forms instead of bilinear forms. First, it introduces two additional projection matrices, W_K and W_V, which allow the model to compute attention logits using a trilinear product of the query, Q, key, K, and the new key, K. This results in a third-order tensor for attention logits, enhancing the expressiveness of the model. The attention weights are then computed by applying a softmax function to these logits, followed by a weighted sum of the value vectors, which incorporates both V and V through an element-wise Hadamard product. This methodology allows the two-simplicial transformer to scale better under limited token budgets, achieving improved performance on tasks such as math, coding, and reasoning compared to traditional transformers.
Can you provide a simple yet illustrative example that demonstrates the inner workings of the two-simplicial attention mechanism? Please walk through the algorithm with this example.
To illustrate the inner workings of the two-simplicial attention mechanism, consider a sequence of three tokens represented as vectors, x equals x_1, x_2, x_3. In the two-simplicial attention, we first project these tokens into query, Q, key, K, and value, V matrices using the respective projection matrices W_Q, W_K, and W_V. For our example, we also introduce additional key and value projection matrices, W_K, and W_V, to compute K and V. The attention logits are computed using a trilinear product, A_IJK equals Q_I CDOT K_J CDOT K_K, resulting in a third-order tensor that captures interactions among the three tokens. The final output is obtained by applying a softmax function to these logits, which transforms them into attention weights, followed by a weighted sum of the value vectors, V and V, based on these weights. This process allows the two-simplicial attention to capture more complex relationships between tokens compared to traditional dot product attention, enhancing its expressiveness and performance on tasks requiring reasoning and coding skills.
What theoretical or practical benefits does the two-simplicial transformer present over traditional transformer architectures, specifically regarding scaling and performance?
The two-simplicial transformer presents several theoretical and practical benefits over traditional transformer architectures, particularly in terms of scaling and performance. Firstly, it demonstrates a more favorable scaling exponent, allowing it to achieve better performance with fewer tokens relative to the number of parameters, which is crucial under token constraints. Empirical results indicate that the two-simplicial transformer outperforms traditional transformers on math, coding, and reasoning tasks, suggesting enhanced expressiveness and efficiency. Additionally, the architecture's ability to generalize the attention mechanism to trilinear forms enables it to approach the irreducible entropy of natural language more effectively than dot product attention transformers. Overall, these advantages position the two-simplicial transformer as a more efficient model for leveraging limited high-quality tokens while maintaining superior performance.
How was the two-simplicial transformer validated or tested in the experiments? Discuss the datasets used, the benchmarks, and the metrics that demonstrate its effectiveness.
The two-simplicial transformer was validated through a series of experiments involving models with varying active parameters, specifically from 1 billion to 5 billion active parameters. The training utilized interleaved sliding window two-simplicial attention, where every fourth layer employed this attention mechanism to balance computational load during pipeline parallelism. The models were evaluated on benchmarks that included GSM-8K, MMLU, MMLU Pro, and MBPP, which are designed to rigorously test math, reasoning, and coding skills. The effectiveness of the two-simplicial transformer was measured using negative log likelihood as the primary metric, with results indicating a decrease in negative log likelihood as the model size increased, particularly noting that models smaller than 2 billion active parameters did not benefit from the two-simplicial attention. Additionally, the experiments revealed that the scaling laws for the two-simplicial attention exhibited a steeper slope, indicating a higher exponent compared to traditional dot product attention transformers, thus demonstrating its improved performance under specific conditions.
What results were achieved with the two-simplicial transformer in terms of negative log likelihood, and how do these results compare to those achieved by traditional dot product attention transformers?
The results achieved with the two-simplicial transformer showed a decrease in negative log likelihood as the model size increased, particularly from a 1 billion active parameter model to a 5 billion active parameter model. However, models smaller than 2 billion active parameters did not exhibit gains from using two-simplicial attention. When comparing the scaling laws, the two-simplicial attention demonstrated a steeper slope, alpha, indicating a higher exponent in its scaling law compared to traditional dot product attention transformers. This suggests that the two-simplicial transformer is more effective in terms of scaling performance under the same token constraints. Overall, while the two-simplicial transformer improves the exponent in scaling laws, its advantages are more pronounced in scenarios where token efficiency is critical.